Last time, no, so we talked about how to prepare alcohols and of course its properties. Do you remember how to prepare alcohols? What are the reactions for the preparation of alcohols? Anyone? There are three usual reactions for the preparation of alcohol. There's a general reaction. What would be usual starting materials when we try to prepare our alcohols? Gonzalez, Arnie, Ronald, anyone? Kadumdum pa mo saan prepare? It's just chapter 8, reaction. Saan prepare sa alcohol? Huh? So chapter 11 is all about alcohols and ethers. I hope okay akong tingog. Before we proceed with reactions of alcohols, no? Before we use our alcohols, we should know how to prepare alcohols, at least theoretically. So what are the common or usual reactions to prepare alcohols? We have already discussed that last time. Ronel? Wala? Wait, tao? Arnie?
Hydrolysis, ma'am, of halides.
Halides, hydrolysis. Pag i-hydrolyze nimo ang halides, I think you will have hydrolysis. Yeah, you will substitution reactions. Yeah, it's possible with the substitution reactions. You can prepare your alcohols. And so wala siya na-include the I can also prepare. What other reactions? What else? So wala na ko na siya na-present last time, but in the previous chapter 56, no? So nucleophilic substitution with your halides. What else? Ronel, any other means to prepare alcohols?
Itong oxymeration, ma'am.
Oxymeration, Maura? Oxymeration sa isumpay.
Oxymeration, decumeration.
Demercuration, and what else? What is the usual from alkene? So what will be your starting material? If you use what will be your starting material? What are the common one? There are other two reactions. Unsa pa? Alimot na mo?
Itong kan, ma'am, hydroboration.
Yes. You have the hydroboration reaction. And of course, you have the acid base. You have the oxymercuration, demercuration, of course. It follows the Markovnikov reaction. You have the hydroboration, oxidation reaction. And of course, the acid catalyzed hydration. So kata yung giingon ka ganina, Arnie, ba to, no? Hydration, it's a hydration. It's a substitution reaction of alkyl halides with hydroxide, but you don't call it hydration reaction. It's a substitution reaction. The hydration reaction is the acid catalyzed hydration reaction of alkenes. Now you don't start with alkyl halides, but you start with an alkene, and you have the hydration reaction. Of course, your catalyst is an acid, and it follows the Markovnikov's rule. And the other one, of course, is the oxymercuration, demercuration. It follows Markovnikov's again, and the other one is the hydroboration oxidation reaction, and it follows the anti-Markovnikov's rule. So only the hydroboration oxidation follows the anti-Markovnikov's rule. And the other one that is mentioned by Arnie, it is the The other way of preparing your alkane is the substitution reaction, which is not mentioned in this slide, this particular slide. But we have mentioned that in chapter 6, I think, we were talking about the SN1 and SN2 reaction. So let's now proceed with the reactions of our alcohols. So, knowing how to prepare alcohols, no? Of course, you have to know when you prepare your alcohols, you have to know what will be your starting materials, what will be your, what will be your starting materials and what will be your reagents. So now we have to also consider how our alcohols reacts when it is present with other agents. And of course, the reactions of alcohol comes from the polarity of alcohols. Now, always you have the OH group, and it can, being polar, always know that it affects its chemical reactivity. Okay, you have an OH, O being the electronegative atom. We have the proton having the partial positive and the oxygen bearing the partial negative charge. And adjacent to carbon to oxygen, the carbon atom would also bear the partial positive charge, being bonded to oxygen, which is partially electronegative. And of course, we've learned that OH is a poor leaving group, and we need to protonate it to proceed with the substitution reaction. Okay, so you have, I think we have already discussed this last time. You have your the reaction of alcohol with a strong acid that always will lead us to the protonation reactions. If it's strong acid, we'll release the electrons and the OH to form a protonated alcohol. And then you can have your protonated alcohol. Once you have your protonated alcohol, it's easy for your alcohol to leave your substrate. This one, okay. We can have this one is easily you can have your nucleophile attacking your carbon, which is partially positive, in a substitution mechanism. And we used alcohol as our substrate when we were discussing about the SN1 and SN2 reaction. And alcohol, we have discussed this one. Alcohol was similar to that of water. In fact, water is a pKa value of around 15.74. Alcohols also has a value of 15, around 15. Tertiary alcohols would have, however, higher pKa value, but smaller alcohols would have pKa value similar to that of water. The difference between 15 and 8 is not so much. And we also learned last time on the relative acidity, water is the strongest, is the most acidic relative to your alcohol, and your alkyne, of course, hydrogen, alkane. And of course, its conjugate base, water will be, the conjugate base of water will be the least basic. And so you would expect that the OR negative, the alkoxide will be more basic than the hydroxide, learned that one. And the alkynide will be more basic than the OR and OH minus minus. And the R minus would be the most basic one. You have to seriously. You have to remember this one. Magawas na siya sa exam. Conversion of alcohols into alkyl halides. Ani is suggested that it's possible, as we have discussed, that from Rx to OH, just have to be mindful of the conditions that to convert the Rx to OH, but it's not the usual pathway that organic chemists would use to prepare alcohol from the alkyl halide, although it is possible that the alkyl halide could also be a starting material to prepare your alcohol. So learn that in the substitution mechanism. And Of course, the alcohol can also be converted to an alkyl halide, and pending na sa atong reagents used. In the ISO 1, you have the HX. HX can be either HI, HCl, HBr, HI, HCl. Okay, and you can also have your PBr3 or SOCl2 if you want to produce RBr, you can use PBr3. If you want to produce RCl or alkyl chloride, can also use SOCl2. For example, you have your tertiary alcohol here, and the presence of concentrated hydrochloric acid at almost room temperature at 25 degrees Celsius can actually substitute OH with HCl here. Of course, your byproduct is water. And to prepare alkyl bromide, can use PBr3, although it's also possible with HBr. But usually they use PBr3 to prepare that one. The yield is just around 63%. So this one is from a primary alcohol. And this one, if you remember your SN1 mechanism, no, this one follows the SN1 mechanism. First, of course, this one is to leave the substrate, no, forming a carbocation. Remember your SN1 mechanism. And once it forms a carbocation, BCl now can then, this one can be protonated from here, can easily leave this, and can easily be substituted with Cl from here. Okay. So the order of reactivity, once you have your HX substituted or your halide substituted to ROH using the HX, can have 3 degree is much more reactive than 2 degree alcohol, than a 1 degree alcohol, and of course your methyl will be the last. In the order of reactivity of hydrogen halides, you have your HI, HBr, and then you have your HCl, and HF is generally unreactive. And of course, what else? If you use sodium halide, there's no reaction actually. It's not possible because it's hard for the OH to leave the substrate, no? In the presence of sodium halide, you don't obtain an acidic solution when using sodium halide. Okay, so you'd rather use, you have to acidify always at one. To acidify that, of course, it's just the same as having your HX at an initial reaction. You can easily protonate your OH here and live to produce your alkyl halide. Again, there is no reaction if there is no acid present, because the OH is a poor living group unless it protonate na siya. When it's protonated, become OH2+, then it's easy to leave the substrate, and it's easy for the reaction to proceed, substitution reaction. The mechanism, the reactions of the alcohol with HX. Let's talk about the mechanism. The secondary, tertiary, allylic, and benzoic alcohols appear to react by a mechanism that involves the formation of carbocation. So this is just similar. Of course, you are already familiar with this one. This one is already discussed in SN1, SN2 reaction. First is the formation of the carbocation, and we need to have an acid. So your acid can come from your hydronium ion. We will use the electrons from the oxygen to form a bond with hydrogen. And of course, you can have the HO bond return back to your hydronium. Now, where does this hydronium come from? Hydronium ion comes from, for example, if you have your HX, in the presence of water, it will dissociate to form H plus and X minus. But your H plus and your X minus, I hope you can imagine what I'm talking about. Your HX, and to form your HX and H minus, Okay, you have your HX, remember? And if you have your would dissociate to form your H plus and X minus, right? And whenever you have your H plus dissociated, of course, in solution, no, it can't stand alone by itself. It's always solvated with water. In the presence of water, this actually becomes, instead of H plus, it's protonated, becomes H3O plus, right? So you expect the acid part can have here. So you have your H3O plus, and this is the one that actually gives the proton to your alcohol. Okay, we use the electrons from oxygen to form a bond, and the covalent bond from here will return back to oxygen. You will recover your water H2O. And then now you have your protonated alcohol. This reaction is actually fast. Once you have your protonated alcohol, this one is very slow, and it will leave the substrate from your carbocation. We have already discussed this in the SN1, SN2 mechanism. And then step 3, of course, is the nucleophile, which comes from your chlorine, from your halide, no? Kani ito nakuha dali. This one, let's say for instance, we're using HCl, for instance, your halide can now attack your carbocation, okay, and it will utilize the electrons from the halide to form a bond with carbocation. So negative and positive, you have this becomes your base, this becomes your acid. And now this reaction is fast, and you'll produce your alkyl halide. And this is a kind of an SN1 mechanism. Remember, primary alcohols and methanol react to form alkyl halides under acidic conditions by SN2 mechanism. This one, SN1 mechanism, if you remember on the reactivity of the SN1 mechanism, it follows by a 3-degree. 3-degree is much more reactive. 3-degree alcohol is much more reactive than a 2-degree alcohol than a 1-degree alcohol, because you will form a carbocation via the SN1 mechanism, right? And having a greater number of alkyl groups that could stabilize the carbocation will lead to a faster reaction. Okay, so the more alkyl groups present, the more your carbocation can be stabilized. And that is the reason, and that is the reason why you have your 3-degree alcohol or 3-degree carbocation is much more stable than 2-degree carbocation than 1-degree carbocation. This for this reason again, that in the SN1 mechanism of the substitution reaction of alcohols with alkyl halides, it follows the 3-degree, 2-degree, and 1-degree trend. Now, 3-degree alcohol is much reactive than 2-degree alcohol than 1-degree because of the formation of this carbocation. Carbocation is much more stabilized when there are a lot of alkyl groups stabilizing your positively charged carbon. For the primary alcohols and methanol forever, there is not so much alkyl groups that would stabilize the positive charged carbon. Okay, so this kind of alcohols react less with alkyl halides even under acidic condition. So instead of following the SN1 mechanism, it instead follows the SN2 mechanism. So still similar to the SN1, the OH, the alcohol, is still difficult to leave even if it follows the SN2 mechanism. So always the first step is the protonation, even if it's a 1-degree alcohol or even if it follows the SN2 mechanism, the alcohol always needs to be protonated because it's very hard for the OH to leave the substrate. So having your protonated alcohol, then your nucleophile, An electron-rich atom or group of atoms can now attack the carbon adjacent to your oxygen, which is partially positive. And once this one utilizes the electrons from your halide, attacks the carbon, and this bonding will go to your oxygen. So balik-balik, this one again is an SN2 kind of mechanism. It attacks from the back, and there is a simultaneous backside attack of your nucleophile to your carbon, and simultaneous bond formation and a simultaneous bond breaking process of your leaving group. This becomes your leaving group, and this becomes your nucleophile. You see now you have your alkyl halide. And water is a good living group, but OH is not. No. It's hard to disperse. It's hard to stabilize your OH minus, minus once it is in solution in water. Sorry. Okay, so another way of preparing your, or another reaction of your alkyl halide or alcohols rather, to form alkyl halides is the use of PBr3 or phosphorus tribromide. Okay, so in this reaction, it follows usual reaction goes with a 1 degree or a 2 degree alcohol. Okay, so the reaction does not involve the formation of the carbocation and easily occurs without rearrangement of the carbon skeleton. Remember that when a reaction follows the formation of the carbocation, there is always a possibility of having rearrangement, right? Like for example, if we start with an alcohol that is a 1 degree or a 2 degree, following the SMN mechanism, form the carbocation. If there is a way, no, if not adjacent alkyl, methyl or alkyl, no, that there is a possibility to form 3 degree carbocation via rearrangement moagi siyang alcohol. But if we use the PBr3, there is no rearrangement, very unlike katong sa previous slides that we discussed here. Okay, so there's no rearrangement and it doesn't involve the formation of the carbocation. That is why there's no rearrangement. And this reaction usually occur, especially if the temperature is kept below 30 degrees Celsius. The phosphorus tribromide is often preferred as a reagent for the transformation of an alcohol to the corresponding alkyl bromide. So for the mechanism, your electrons or the oxygen will attack the phosphorus. And nang-attack man niya si phosphorus. Phosphorus is connected to 3 bromines, okay? And bromine, of course, bears partial negative charge, being more electronegative than phosphorus. So kaning tulog ka bromine will bear the partial negative charge. And you expect this phosphorus to be partially positive. And in this group here, you will ask, asa man ang partially negative charge na atom? Of course, it will be the oxygen being an electronegative atom. So the partial negative oxygen will attack the partial positive phosphorus, and there will be a bond formation going on, and it will proceed to have a bond formation between oxygen and phosphorus using the electrons gikan sa oxygen. So if we use the electrons gikan sa oxygen and phosphorus, okay, makuha ang isa ka lone pair, and there will be a bond breaking here. Once you form a new bond with phosphorus, so you have your Br minus. When you say Br minus, there is 2, 4, 6, 8 unshared electrons here. And for oxygen, kay gamit naman to form a bond. I-follow ninyo, kay gamitan man nato ang duha ka electron pair, right? So mawala na ng lone pair diri. Kay gigamit nato. So isa na lang ka lone pair of electrons. And then because oxygen has 3 bonds, not by positive charge sa oxygen. Always know that whenever oxygen has 3 bonds, na siya positive charge mo to. Si protonated alcohol, di ba? Na siya positive charge because of oxygen na ay 3 bonds. And of course, again, kung makalimot mo, just calculate on the formal charge of oxygen and on the positive. Okay, so once you have your protonated alkyl dibromophosphate, kani siya. Okay, so what will happen? This now becomes this group, kani COH with PBr2 with dibromophosphate, kani now becomes a good living group. No, na siya reason bitaw to leave this one because oxygen becomes partial, becomes positive, no? So na siya driving force. The driving force is to stabilize the develop positive charge ng oxygen. Nga naman si oxygen dili niya kaya to bear a charge nga positive. Nga naman oxygen is an electronegative atom. So it always want to disperse the developed positive charge here. And the only way to disperse this positive charge here, that would be the driving force, kailangan na to i-disperse ng positive charge. So kuhaon niya ning electrons gikan sa carbon-oxygen bond para mobiya siya. Right? So gamitin na niya ng electrons gikan sa carbon-oxygen bond, pirahon na niya, and would convert that one to it becomes a good living group, and it happens when this nucleophile, the bromide, you can will attack your carbon here, and once it attacks, it's easy for this to draw the electrons to leave, bearing with it the electrons you can bond. And so now you have your R carbon and bromide, and plus your PBr and POH. Okay, so instead of bromine, one of the bromine is substituted with OH. Now, another reaction of alcohol is with SOCl2. And again, this one, we use SOCl2 and PBr3 when we are using a 1 degree or 2 degree alcohol. Okay, so what happens? As with PBr3, the reaction does not involve the formation of carbocation and usually occurs without the arrangement of the carbon skeleton. So pyridine is often included to promote the reaction, and what happened? Pyridine is the usual solvent. So what happens? Again, you check in here your sulfur, nganong kaniman ang ma-attack, no? What happens is that your oxygen dili ang araw sa ni-imove. It's not the hydrogen that would attack. It's the oxygen. Let's see. Okay, na-move na siya. Okay, let's go back to the mechanism of the reaction of SOCl2. No. So again, we look at the structure of SOCl2. We know that for the alcohol, oxygen will bear the partial negative charge, right? Being an electronegative atom. So oxygen being an electronegative atom will always have to look, this is our nucleophile, we'll always have to look a positive center, an electrophile. No? So it's the ring reagent, tanaw na to, which one will bear the charge, positive. So oxygen is an electronegative atom. It bears a partial negative charge. Chlorine also is an electronegative atom. It bears a partial negative charge along with this other oxygen. So natabangan si sulfur, right? It's being attached to a more electronegative atom than itself. So this one bears a partial positive charge. So because of that, the oxygen will attack sulfur and it will utilize the electrons from oxygen. And once it attacks, what will happen? Manubra man of bonds, so far, no? The one bond, sulfur oxygen, will be converted back to oxygen. So you have here. And once oxygen forms a bond with another atom, having already two bonds, mahimo siyang positive. Ganong positive, oxygen has three bonds and an electron pair. If we calculate again on the formal charge of oxygen, group number of oxygen is 6 minus number of bonds. The balance of oxygen is 6, or it's the valence electron of oxygen is 6, or its group number is 6 minus number of bonds 3. So 6 minus 3, 3 minus number of unshared electrons 2. So 3 minus 2 is positive 1 or 1, and that is the formal charge of oxygen. And so for here, would have a zero charge, formal charge. With the oxygen, there is a 6 unshared electrons, or 3 lone pairs and 1 bond. It will bear negative charge. So there. So the overall charge of this compound is 0. Formal charge, positive and negative, but it's identified now that oxygen would bear a partial or a positive charge. So what happens is that to stabilize this one, oxygen will form another double bond again, and once it forms a double bond, chlorine will be forced to leave the group. So what happens, you will have your ROH SOCl. Okay, and look at on the formal charge, we have a positive formal charge, and the chlorine will bear a negative for the overall charge here. So nakay plus Cl minus. So this one is positive, protonated COH, okay, so alcohol, and you have a Cl minus. So now because of that, pyridine can easily abstract the proton. Pyridine, that's the structure of pyridine. It's a 6-membered ring, and it's aromatic, no? And there's nitrogen in the structure. So 1, 2, 3, 4, 5, 6, and there's an alternating double single bond. And there is a lone pair kang nitrogen. Okay, so si nitrogen, gikan kang pyridine, would act as a Lewis base, and it will deprotonate si alcohol, no? And what will happen is that to obstruct the proton here, to obstruct niya, it will utilize the electrons. And pag attack niya ang proton, the bond between hydrogen and oxygen will be converted to a lone pair. So you will have your N, dapat na siya NH, protonated na siya dapat, and you have your ROSOCl. So mawala na ang charge here. So it becomes protonated dapat in H, but it will be abstracted again. Should have an NH here. Pyridine. So once you have that, what will happen? For the other molecule of pyridine, it will now attack the partially positive sulfur here. There is a partial positive sulfur here, and you will attack this one, and it will utilize the electrons given from pyridine. And once you do that, the electrons, the same thing that would happen earlier, the electrons comes from the bond will be converted to an unshared electrons, and pag mabalik siya, okay, to stabilize this one, because oxygen would want to be stable, so we need to stabilize its negative charge, so ibalik ra pud na niya. Okay, pagbalik niya to form a double bond, this one now will leave. Pare sa ning kanin, right? Pag-attack niya diri, balik siya dito, nakay kanina. But oxygen is negatively charged. It needs to disperse its negative charge. So ibalik rin niya to form a double bond para ma-disperse ang charge nga negative. Okay, ma-disperse ang charge nga negative, mawala ang negative na oxygen pag na siya'y double bond, no? It will have formal charge na 0. But ang mahitabo is si chlorine na lang ang mo biya. Like this one. So parehas pa na, no? Ni-attack siya din, ni balik siya dito, or ni balik kapit siya, ni himo siya lone pair, or ni balik kapit siya og double bond. Pero pagbalik niya ang double bond, matanggal na si chlorine. Okay? So, ito ha. So, kung matanggal na si chlorine, what will happen is, nakay nitrogen, sulfur, tanggal man si chlorine, okay, you have SOCl. Okay? Plus chlorine minus na sa diriya, plus Cl minus. Ano siya? So once you have your ROSO, your Cl can now attack your R. This one, oxygen can now would now be a good living group, no? Because it's already bonded to sulfur here, where it can be helped stabilized by this group. What happens? The carbon here attached to your oxygen, of course, is partially positive. So here, the chlorine that's being eliminated, which is a nucleophile, it's rich with Cl low electrons and negative charge can now attack the carbon weakens out here. And then you will have your RCl. And what happens once it attacks, the bond between carbon and oxygen will go to oxygen. So you have a negative charge here. And this one can be dispersed by electron delocalization. So diba si oxygen na siya negative charge, it wants to disperse a negative charge. So gamitin na niya to form a double bond. Pag gamit yung double bond din na kanina po siya ang mahimo na single bond. So there will be a resonance structure here. And this one, that is the reason why oxygen being bonded to this group is much more stabilized than OH lang gid siya. That is the reason why SOCl2 is usually used from 1 degree or 2 degree alcohol, pero partner siya with pyridine. Okay, pyridine is this one.